Assalamu alaikum. My name is Daiyan Khan, and today me and my groupmates are going to be presenting chapter 10 of a book named Designing Distributed Systems, and the name of the chapter is Work Queue Systems. As you can see, this is the concept map of our chapter.
Assalamu alaikum. I'm Sanowar. Let's start with work queue. The simplest form of batch processing is a work queue. In a work queue system, there is a batch of work to be performed. Each piece of work is wholly independent of the other and can be processed without any interaction. Generally, the goal of the work queue system are to ensure that each piece of work is processed within a certain of time. Workers are scaled up or scaled down to ensure that the work can be handled. An illustration of the generic work queue is shown in figure 10.1. Okay, let's talk about a generic work queue system. The work queue is an ideal way to demonstrate the power of distributed system pattern. The most of the logic in the work queue system is wholly independent of the actual work being done, and in many cases the delivery of the work can be performed in a independent manner as well. To illustrate this point, consider this work queue illustrated in figure 10.1. If we took a look it again and identify functionality that can be provided by a shared set of library contents, it becomes apparent that the most of the implementation of a containerized work queue can be shared across a wide variety of uses as shown in figure 10.2. So building a reasonable container-based work queue requires the definition of interface between the generic library containers and the user-defined application logic. In the containerized work queue, there are two interfaces: the source container interface, which provides a stream of work item that used processing, and the worker container interface, which knows how to actually process the work item. So our next topic is the source container interface. To operate, every work queue needs a collection of work items that needs processing. There are many different sorts of work items that work queue depending on the specific application of the work queue. However, once the set of items has been obtained, the actual operation of the work queue is quite generic. Consequently, we can separate the application specific queue source logic from the generic queue processing logic. Given the previously defined pattern of the container groups, this can be shown as the example of the ambassador pattern defined previously. The generic work queue container is the primary application container, and the application specific source container is the ambassador that proxies the generic work queues requested out to the definition of the work queue out in the real world. The container group is illustrated in figure 10.3. And there are many cases where an asynchronous process execution context is needed, and the work queue API is the most commonly used mechanism for this case. Given this coordination between the generic work queue manager and the application specific ambassador, we need formal definition of the interface between the two containers. Here is an example. You can see here returns a complete list of all items, and it provides the detail of the specific item. The item details are obtained from this API, and the item.data defined is processed along to the worker interface for processing.
Assalamu alaikum. My name is Redwanuzzaman. ID 211660001. My topic, the worker container interface. Our generic second container interface was of work, and there were work of container and interface are simply different than the provides work source interface for several reasons. And there are two types of API system query, and there are first of all it is one of API and a single call to start work and no other API call in the lifetime of the worker container. And secondly, there are worker container is not within a container group with the job row manager. And there are few key points of our API system, and there are first of all we may need to take extra security protections to prevent any malicious user in our cluster from injecting extra work into the system. And there are addition to the job role source API. We used a simply HTTP based API to return items to the job row manager. And there are result we will use a file based API for stuff containers. And there are ideally, and this is API can be applied via a Kubernetes config map object, the object that can be mounted on a container group as a file. And there are shown in figure 10.4, and these are figure, and there are work container group and this worker container implementation, and there are Kubernetes API and this work item data config map and this config map volume. And there is implementation file based API pattern is also easy for container implementation. And and there were two with the implementation of Java query source. Most stuff containers will be specific purpose container image designed for a specific job role application. But there are also general stuff that can be applied to multiple different job role application. And there a container can be mostly generic but may have a specific script to implement it as return runtime parameters, and those most tasks can be shared by multiple users and work of file handling, and only it specific issues need to be provided by the end user of file processing. And these are API queuing system work.
Assalamu alaikum everyone, I'm Md Muyeed Shahriar, ID 211411044. So in this chapter we're going to be discussing the work queue infrastructure of this algorithm. So given the implementation of the two containers that described previously by my group mates, the only thing left is to implement it. So the basic algorithm looks quite straightforward, at least from the written point of view. So we're gonna load the work into a container, then we're gonna determine which work has been processed and which are not. Then we're gonna be processing those works which are not processed yet. Then we're gonna spawn some jobs for the workers, then assign them to them, and if the worker contains finishes successfully, then record the work, and if not, we're gonna go back to and bring process the other thing. That's pretty much it. So having said that, is straightforward on the written document, but actually implementing this algorithm is quite difficult. but fortunately Kubernetes container orchestrator contains a number of features that makes this job significantly easy to implement, because now Kubernetes contains a job object that allows the reliable execution of the work queue. So every resource you got, that's gonna be used in a very efficient way. Additionally, Kubernetes has annotations for each jobs, so it marks each job and the work item, uh, the what work item it's processing right now. That's enables us to understand which items are being processed and which are not. So if we want to see the core backbone of this algorithm, we can see that it's again straightforward. Get the list of the job item from the source container, then create some jobs to assign, then differentiate between the items that haven't been processed and push them for the processing. mm, and basically for the unprocessed items, create a new job and spawn container. That pretty much it. So if we want to look at the code itself, this is a snippet of the code. It's a just simple Python script that can implement work queue. So if we start here, config. It's basically gonna load the config, then create a batch with the workforce, then it's gonna push the batch into the update queue. And if we come to the update queue here, we can see it's getting the response, then creating an object, creating items. Then if it's gonna search for which items are not being processed and which are processed. If the metadata, which, because I said Kubernetes gonna giving a flag to each work. So if it's found that this variable here found, it's gonna actually flag it. So if it's not found, we're gonna make a job here and push that item we created here with the items object, then push it to the make job item, then make the job, create an object, and at the end of it we're gonna make a new container with the item and object, and then push it to here, and it's gonna just basically finish the rest of the work and return the container back to and said that it's the work is done.
Assalamu alaikum, sir. I am Md Mamun-Or-Rashid. My ID is 211660005. Now I am going to deliver my presentation, which topic is hands-on implementing a video thumbnailer. To provide a concrete example of how we might use a work queue, consider the task of generating thumbnails for videos. These thumbnails help users determine which videos they want to watch. To implement this video thumbnailer, we need two different user containers. The first is the work item source container. The simplest way for this to work is for the work items to appear on a shared disk, such as a network file share system, that means NFS share. The work item source simply lists the files in this directory and returns them to the caller. And here is a simple node program that does this. This source of defines the queue of movies to thumbnail. We use the FFmpeg utility to actually perform the thumbnailing work. And we can create a container that uses the following as its command line. This command will take one frame every 100 frames and output it as a PNG file. We can implement this image processing using an existing FFmpeg Docker image. The FFmpeg Docker image is a popular choice.
Assalamu alaikum, this is Daiyan again, and I'm going to be explaining the dynamic scaling of workers. The types of work queues discussed by my teammates may not always be the most efficient, because they may end up spending a lot of resources on idle processes. We can address this issue by limiting the work queue. This can be achieved by limiting the amount of processes that are parallelized, which will also limit the maximum resources used at a point in time. However, a drawback of dynamically scaling the workers is that this may lead to high latency under heavy workloads, and it's not an easy to downsize work queues. We've seen that this chapter mainly focuses on the use of containers for the purposes of reusing code. This can also be applied to work queue patterns, in which instead of writing the same code multiple times, we can reuse certain general patterns of queues via these container methods, leading to the multi-worker pattern. To be able to carry out this form of reuse of code, we can use a multi-worker pattern, which is actually a specialized adapter pattern. How this pattern works is by unifying separate work containers through reusable containers, which means that implementers of the code have to put in less effort as previous code can be reused. That concludes the topics discussed in this chapter. Thank you for your time.